So now for the discussion part of this phenacetin. As always, it's kind of nice if we have a mechanism that, it's in McMurray and it's a pretty easy one to follow, standard. It's always good to write it out first. Kind of helps along with, near the introduction, an example energy diagram where we can talk about intermediates or things like that. So what we have is you treat it with carbonate and it deprotonates it. And supposedly is a good chance, and it sounds like it makes sense, you're going to have some of this intermediate anion. It will then attack iodoethane to make your product. This step is very much an SN2. So if this is true, then this intermediate, we could definitely say, and it does kind of stand to reason, this is a very well-known, that's a phenolic hydrogen. So it's very well known that this has no problem existing partially dissociated. So the chances of having some of this in solution is actually very, very likely. So it makes sense that we're going to have an intermediate spot for that. As far as potassium carbonate, it's not a super reactive thing. It's not like thionyl chloride, which we know would be sitting way up here. And when it starts reacting, it will give off lots of energy. This one, hence the question marks, not sure what it be. However, as far as the organic pieces are concerned, in Mother Nature's Energy Bank Book, it would look similar to something like this. Ether functional groups are supposed to be more stable than this, so you can see how that one's sitting just a little lower than the starting material functional group. So, did we see or feel an exothermic reaction happening quickly? Right? I myself cannot recall if it evidently was heating up. On the scale we did it, it's so small, so there's a couple things that could be done here. On an industrial size, if it was even a slightly exothermic reaction, on such a large scale, you would definitely start seeing the heat and the temperature rise without even refluxing it to start. The problem with that too, though, is some of these thermodynamic concepts, such as exothermic, initial and final, that is called a thermodynamic quantity. The kinetic is the height of the hill. You can have very exothermic reactions, but they happen so slowly that you don't actually feel the heat come on board. So to officially determine this, you might have to use a calorimeter, even if the industrial scale doesn't let you feel your mixture getting cooler, which would mean endothermic, or heating up exothermic. As far as the TLC, and also just jump right to this one. If you took your TLC before you put everything in the SEP funnel and did a treatment at some point with sodium hydroxide, the purpose of the sodium hydroxide in treating it, so after the separatory funnel, this is the classic way it looks. Your starting material, which is the alcohol, sticks to the gel. Your product, having put an ethyl group on there, should move faster. So sure enough, if you've already done your complete separatory funnel work, the OH washing usually removes all starting material if there's any left in your reaction, so you won't see any here. If you took the TLC before the SEP funnel work, and any of those students who did, you will see some leftover starting material. So it's a very important piece of information. If you went through the reaction this way and had an 80% yield, you might think the reaction went great and there was no starting material left over, when in fact, this proves that there absolutely was. So just like all reactions in the classical sense here, when you do some sort of separation in industry, when you're trying something new, you can take your organic layer, rotovap it, and you can weigh out the product. NMR will tell you how pure. But the question always remains, how much organic material would be left in this aqueous layer? So in industry, the typical thing they do is take that aqueous layer when they're done, run an HPLC just to see starting materials and products that could still be left in it. And that gives you more accurate actual yield for the reaction. And what types of things processing to get your product isolated and pure you'd have to do. The yield, and the thing I just mentioned heads into the yield conversation here. Depending where you sat on the fence here, what your TLC showed, compared with what we know should always be done, you might have to adjust your yield. I think most people get between 60 and 80, and that does seem normal. This reaction, though, if you account for anything left over in the aqueous layer, the yield is actually usually 90s. So the question in this experiment is just finding out where the missing organic material went to. So other than that, folks, that's just a really quick covering of the normal fundamental pieces of a discussion. The rest, or any additional observations you've noticed, you can talk about it, such as if you're left over in your NMR with MEK or iodoethane, and obviously it was not rotavapt enough, you could do a correction on the yield, or come and see me if you have any other questions.